Welcome to this webinar organized by Sofix and Dolphin Semiconductor. Today we will explore how to optimize IoT SoCs with ESD protection and power management IP to design more reliable systems on chip. You will discover how Sofix and Dolphin Semiconductor are working together to enhance IoT SoCs with cutting-edge interface and power management solutions. You will learn how ESD protection and power management impact SoC design, how to choose the right IP blocks for your next IoT chips, and see a real-world example of power management network for SoCs. By the end of this webinar, you will have the key insight to make your designs more efficient and reliable. Now let's introduce our speakers. We are pleased to have Hakim Jafar, VP of Marketing and Support at Dolphin Semiconductor, and Bart Kippens, Chief Business Development at Sofix. Together, they will share their expertise in this webinar. Thank you.
Thank you, Charlotte, and hi, everyone. As you get it today, the topic we want to touch is related to IoT chips and IoT design chips. So when designing a device that is targeting IoT, that is most of the time wirelessly connected, what you want to make sure is if they are battery operated, that they are what we call low power operation mode. They feature such mode that can extend the lifetime on the battery and therefore enhance the user experience. You want to make sure that as well the connectivity is robust enough and make sure that you got the coverage, whatever is located your device. If you do a sensor, for instance, in a house or in a building, you want to make sure that communication is okay. There is also a bit of power computing that is necessary, especially when you have a CPU that need to compute sensor or do a sensor fusion activity. And most than everything, your device must be robust against ESD and EOS. I would like to insist on EOS, which are the electrical overstress. Everybody is pretty well familiar with ESD, but EOS has a lot of importance when it comes to designing a device. Our experience that we bring here, Dolphin Semiconductor and Sofix, is first selecting the right DC to DC NLDO solution for a low power device and a wireless device. You know that DC to DC can generate a lot of noise that can disturb the radio or any ADC analog converters. And here we have a pretty good solution, and there are some really points to take care about. And as well, any device has really to be ESD robust enough. Otherwise, the device will match a lot of, will find a lot of issue down the mounting, on the soldering of the part during the lifetime of the product. So really, those are two key aspects that are impacting any device, and more specifically any IoT chips. So here, what we want to share with you is the kind of benefit you will get working with Sofix or Dolphin Semiconductor IP portfolio. First of all, combining our knowledge and when we talk together when preparing this video, we realized that we are both working with leader manufacturer of SoC in low power, whatever low power MCU, whatever sensor network. We're also working together with key players in the wireless market, right? Whatever Bluetooth, classic or BLE, Wi-Fi, NFC, GNSS as well. All those applications that could be battery powered and are really noise sensitive. But we realize as well that an important DC to DC as well as ESD protection is key actually for AGI device. You know, AGI device could be from I would say the simple product that is doing predictive maintenance up to high computing power multi CPUs. Therefore, the current that both animals will request, right, from a power management unit is going to be completely different. One may request 100 milliamp, while the other one can go 4 amp, 6 amp, or 8 amp. And therefore, the DC to DC or the LDO you're going to design is going to be completely different. The ESD impact is going to be completely different. And both together, with two companies, we offer solutions that are capable to support from the low end to the high end solutions. Okay, so let's go a bit deeper here. This is a typical block diagram of a microcontroller. Could be any of the well-known microcontroller, a 32-bit one, for instance. So any product is fitted into a package, right, with a lot of pins, and what matters is the efficient pin count. So what I mean here is in a package you may have pins that are for the power supply, like VDD, pins related to the clocks, and usually with those pins you cannot use them as a traditional GPIOs or analog pin, for instance. Therefore, what you want to do when you design such product is to make sure that you have a maximum efficient pin like GPIOs. I give you an example. If you design a wireless product on a 28 pin package, you will have some pin dedicated for the RF and so on, maybe 10, maybe 15. Therefore, on a 28 pin package, you have only 13 pins available, right? What if you can get more? What if you can get 15, 17, 20? And the typical power management IPs you're going to use can help in that aspect. I give you an example. Here in the block diagram we see the product we see can support 162 up to 55. This is key because most of the product today are battery powered and therefore need to be recharged. I take an example of the earbuds. Earbuds are stored in a case, and this casing is usually plugged to USB to be charged. And USB therefore is for 5.5 volt. So if you design this with a 3.6 volt product, therefore you will need a little piece of hardware between the VDD of your USB and the VDD of your product. So having a product that can do this is going to reduce your BOM cost, right? So less external component. So you don't pay for the component, you don't pay for the mounting, you can reduce the size of your PCB and so on and so on. It's not the only thing. So here you have a super DC-DC that can do 162 5.5 volt. Below this DC-DC here, you see there is a capless LDO. And here is one of the axes how we could help optimizing the number of pin count. Capless LDO is an LDO where you don't need an external capacitance. Therefore, you save the pin on the package on which you should plug the capacitance. So you save the pin, you can use it as a traditional GPIOs, and you save the cost of the capacitance and the mounting. And this capless LDO is power enough to power all the logic you have, a CPU, a DSP, your memory, and so on. As you can see in the same logic block here, just below we put what we call Meerkat. Meerkat is one of our IP, it's an in-situ monitor. And you may say, okay, why do you use this? Actually, it's pretty simple. So what we realize is on some computing devices, high computing or energy care device, usually there is a lot of guard band or over design. And most of our customers, they told us, look, I'd like to get the best of the performance I have with the energy I'm supplying to the digital. So Meerkat is, to make it short, is a sensor that will help you actually to boost the frequency in order to extend the performance, for instance, of computing with the same energy. So you will have some flags, and then when you will reach the limit, you're going to have some flags or maybe alarm, and then you know that you have somehow overclocked, if I can say it like this, overclocked the device. But it works also in the other way around. You may say, look, I'm happy with the performance, now I just want to reduce the power in order to increase my power saving. Therefore, you're going to reduce the voltage of the digital and still monitor those flags and error signals in order to say, okay, this is the lowest level I can reach in powering the logic with still an acceptable performance and without any degradation of the signal. So we see the DC-DC can power this, but then also our DC-DC can directly power any analog block, whatever radio, it could be BLE, Wi-Fi, all the analog. And here it's interesting because we all know that RF is very sensitive to ripple and noise given by a DC-DC, and usually you have a direct LDO from outside that is directly powering the radio. While here, because we have a specific design and a special care about ripple and noise on the DC-DC, we can directly power our the radio by a partner, for instance. And I invite you to look at our section partner to see where you can get many radios. But also on the ADC, ADC are very sensitive to the noise. And when you do conversion, if it's directly tied to a DC to DC, you may have some error while converting. I take the example of audio, for instance. So when you do audio, you may have this kind of issue, but our DC to DC has a special care about analog, and more than this, has a specific feature to support the audio grade ADC and DAC, right? Because when you do audio, you have the range of 24, 25 kilohertz, which can be a killer actually in the audio quality, and our DC-DC is designed to manage such issue. So this is for the central part. Now on the right part of the block diagram, you have this LDO, this big LDO that can supply all the peripherals actually that could be power demanding, like PCI controller, USB, Ethernet, and so on. So this LDO, you have plenty of flavor, can support 2, 3, 4, 400 milliamp up to 1 amp, right? Therefore, you can get enough current that you need. And now on the left side of this block diagram, what we see is a micro LDO. What is a micro LDO? Is an LDO that we're going to use to supply and to power what we call in the microcontroller or device AON, always on domain. This domain is the part that you're going to keep alive when shutting down all the rest to save the power. So if you look at the microcontroller, most of them have the name like standby, stop, hibernate, sleep, or deep sleep, or stuff like this. So in this domain, what we call always on domain, you're going to have a power controller. Usually you can have some memory retention like the RAM. And most of the time you're going to need an RTC. And the RTC, the real-time clock, is going to be powered or clocked, I would say, by a 32K oscillator or a 32K crystal, right? Which both are available at Dolphin. The thing is, if you are still in the thinking of reducing the BOM cost, you may say, how can I get rid of a 32 kilohertz crystal? And here we're offering a 32 kilohertz oscillator that is capable to support or to sustain 300 ppm accuracy. Therefore, if you take the example of a Bluetooth device, you can get rid of the external 32 kilohertz crystal and still be capable to shut down your device or to put it in standby and wake up the device and still be in the right window of connection for the BLE, right? So you can remove the crystal, save the cost of the crystal, and still have a device that can support BLE or Wi-Fi connection. So now if I want to make a kind of recap of the things that you may need here and that are key in terms of power management to design the product. So as we mentioned, an always on that is capable to be at sub 1 microamp actually power consumption. A DC to DC, as we mentioned, a fourth generation. I have to tell you that at Dolphin Semiconductor, we're doing analog IPs since more than 2 decades. So this is our fourth generation here with a wide input voltage. We really think and see a trend actually with a 5.5 volt. Rather than having 2 DC to DC, for instance, as many other SoC designer do, here you have only a single one that do 162 5.5 volt. It means that in terms of pin count, you will use only 3 or 4 pins rather than 6 or 8, right, to do the range 162.55. Super low quiescent current. In terms of efficiency, this DC-DC has a 93% efficiency when loaded, but most important, the efficiency is still 73% at super low load. Usually a DC to DC is efficient when it's loaded or efficient on low load, right? It's designed for one or the other, usually when you load it. But here we still have an IP that is efficient whatever the condition. It is super low area actually, and it has a super low ripple. We have a lot of flavor of LDO, right? That will help you to design the best product with low quiescent, fast transient, the capless, which is key to save pin count. And as we mentioned, we have what we call the in-situ monitors. That is the perfect sensor actually to enable any AVS system. AVS is adaptive voltage scaling, because in order to be capable to adapt the voltage scaling outside on the fly, what you need to have actually is make sure that you can sense very quickly actually and react very fastly. Okay, so I think we got the message here for everything related to the power management unit. Now I'll leave the floor to my friend Bart that will tell you much more about ESD, because when you design all this with all those DC-DC, LDOs and so on, you have to make sure that you have a key ESD protection, otherwise you're going to get in trouble when mounting during the lifetime of the product, and that's why you need key and bulletproof ESD protection. It's your turn now.
Thank you, Charlotte and Hakim, for the introduction. So when you design a chip, most of the time you get I/O libraries from the foundry, and such I/O libraries, they contain like power and ground cells for core and I/O domains, digital I/Os, and also analog I/Os, and maybe filler and corner cells. And for many applications, using those libraries is good enough. However, if you are designing, for instance, IoT or consumer or wearable applications, most foundry libraries introduce some limitations. For instance, limitations could be that the I/O range is fixed in the sense that, yeah, maybe it only goes to 2.5 volts, while people still need higher voltages. Frequently, the I/Os from the standard library introduce a lot of leakage. They also are designed for a fixed ESD robustness, for instance 2000 volt HBM. They come with limited flexibility. For instance, if you have requirements to have over voltage tolerant interface, that's not always possible in the standard I/Os. If you are designing high-speed interfaces, then the parasitic capacitance of those foundry I/Os can be too high. And in total, following all of the rules, then it can come up with quite a large area for all of these blocks together. So based on our experience designing IP for applications like consumer applications, IoT, Internet of Things, and wearables, we have developed solutions which have certain benefits and to basically prevent those limitations. So for instance, we have developed solutions which have much lower leakage. For instance, comparing standard ESD protection with the Sofix ESD, we can have 100 and sometimes 1,000 times lower leakage, which could be important for instance, battery powered applications, or applications that actually do not use a battery and just rely on ambient energy, like the recent cooperation with Onyo. Also, for wireless applications, the leakage at the interface, the lower the leakage, the better the LNAQ factor. And it can also improve the stable offset of sensor interfaces. Another aspect is parasitic capacitance. So if you are designing high-speed interfaces or wireless interfaces, typically people require low RC, no input resistance, and low capacitive loading. Additionally, typically you have to protect core devices to enable such high-speed interfaces. And so on this graph, you can see first, maybe on the right side, if you are using the same ESD performance, for instance 2000 volt HBM, we can reduce the parasitic capacitance of the ESD by 30 and sometimes 50%, enabling maybe a higher bandwidth for your interface. Or on the other side, you could say if the parasitic capacitance is fixed, let's say 100 femtofarad, then Sofix can provide a higher ESD robustness level. Another thing, as I mentioned, area. So by using Sofix ESD and I/Os, there is an opportunity to save area of the full chip. We provide ESD clamps, for instance, for power and rails clamps, but also for local protection, which are much smaller than the traditional approaches. And by reducing the number of power clamp cells, for instance, a larger distance to the I/O interface or a larger distance between power clamps themselves, we can also reduce the total area. Yeah, as I mentioned in the intro, sometimes the Foundry library is limiting companies in the amount of the level of voltage levels that they can use. And sometimes you need higher voltages, for instance 5 volt or 3.3 volts. Sometimes you need to enable over voltage tolerant interface like I2C, where you cannot allow a diode, ESD diode between I/O and VDD. And sometimes the voltage has to be lower, so maybe I/O voltage starts at 1.8, but people want to build interfaces at 1 volt or lower. So that's also something Sofix can support and has supported in many applications. So for instance, if you look at this graph, so starting from on the right side 0.13 going down to 40 and then eventually 2 nanometer, there is what we call a Vmax, the maximum voltage defined by the let's say I/O library. And initially in 0.13 it's more than 5 volts, but going down to 2 nanometer, actually it's about 1 volt. And so you can have I/O cells provided by the foundry typically below the Vmax line, for instance 1.8 volt in 7 nanometer, that's available, but people that we talk to still require, for instance, 2.5 volt in 7 nanometer or 3.3 volt in 22 nanometer. And so Sofix can provide I/Os above the Vmax line. And we have done such applications for different projects. And then finally, sometimes the ESD robustness needs to be different than the standard one. The traditional GPIO library comes with, for instance, 1 kV or 2 kV HBM robustness. We have worked with all kinds of applications, and sometimes you need much higher, even higher than 6 kV shown on this graph. For instance, for multimedia interface, HDMI, USB, timing controllers. Typically also medical and automotive applications require higher ESD robustness. And sometimes it's okay to have a reduced ESD robustness. For instance, for high-speed interfaces, people sometimes can reduce it below 1 kV. And certainly for die-to-die interfaces, it's possible to reduce maybe to 200 volts or 100 volts HBM. And of course, for this discussion, I talked mostly about HBM, but similarly for CDM, we can help you to have high ECDM, or for die-to-die, maybe less than 30 volts is enough.
Wow, great stuff, Bart. Thank you for sharing all this with us. That's really amazing what you guys have in terms of technologies. As a takeaway, people, as a takeaway of this video, 4 simple bullets actually. The first one is you need innovative product actually to boost your design, right? You need to make the difference, and here Sofix and Dolphin Semiconductor are offering really key features for you to make the difference. In power management, we have seen it. You have top-notch IP actually to help you building crazy product actually. The robustness of your product are really is going to be strengthened with Sofix solution actually, and we've seen this the common customer we have, really those guys have a rock product, and what you get working with us together is really the know-how of the two company, right? One is a leader in the ESD, and the other one is lead in power management and analog converters. What you get is all this knowledge actually combined in a single offer. So I'd like to thank you. Thank my friend Bart for co-presenting this slide set, and I hope you guys will have learned a lot of things, and feel free to contact us, and take care. Bye bye.